Let us now consider the case of building confidence intervals around sample proportion for an estimate of the population proportion. So the big difference from what we have done in the case of mean is that we will always be using the z distribution. Let's say that p bar is the proportion from our sample, and the standard error of sample proportion is the square root of p bar times 1 minus p divided by n. So this is our standard error of the population proportion, and alpha is our desired level of significance. So we are looking at the area of alpha by 2 on both tails. So we'll look at the corresponding z value, which gives us the z score for the area in the tails being alpha over 2. And just like we can calculate the desired sample size to get a confident interval with a certain margin of error, we can do that same exercise for proportion as well. So if we are given the population proportion, we can simply plug this in here to get the sample size, which will give us the desired margin of error E. Around the sample proportion, we would take our desired z stat of alpha by 2, then squared, times p times 1 minus p, and then divided by our desired margin of error. What if we do not have any prior on p star? Well, the most conservative estimate, which gives us the largest sample size, would be to assume p star equal to 0.5. So if we do not know p star a priori, we can take the planning value of p star to be 0.05. Otherwise, the problem will then give us the value of p star. To see an application of this, consider the case of a ski resort, ice chalet, which offers beginning skating lessons. And they're interested in figuring out, in the age group of 8 to 12, what is the true proportion of girls in their ski lesson classes. So let's say they conduct a survey of 80 students at random, and they find that the number of girls in that survey is 64, and the number of boys is 16. So we can first calculate the proportion, and this is a sample proportion, and we will use this to get an interval for the true proportion of girls in the beginning skiing class in the age groups of 8 to 12. So let's first calculate our sample proportion, which is given by our number of success over number of failure. Our success being girl students would be 64, and our failure and total sample size is 80. This gives us our p bar, or proportion of success, to be 0.8. And then our 1 minus p bar, which is the proportion of failure, would be 0.2. So now we have to construct a confidence interval of 95%. So what we can first do is we can calculate the standard error of the proportion, and this is given by the square root of p bar times 1 minus p bar divided by n. So in our case, it would be 0.8 times 0.2 divided by 80, and then the square root of that. And this is equal to 0.0047. 0.0447. So this is our standard error of the proportion. To construct a 95% confidence interval, our alpha is 5%, which implies that our area in the tails would be 0.025%. 0.025 or 2.5%. So we can construct the confidence interval by adding and subtracting the margin of error from our proportion, and this margin of error is given by our corresponding z value times the standard error of the proportion, which is p bar 1 minus p bar divided by n. Our p bar is 0.8. We can calculate the z bar from either the TI-84 calculators or from the distribution calculator in JMP. we can use the jump distribution calculator to obtain our z. We'll choose the normal, and we are inputting the probabilities to obtain the z values. And our probabilities, or our central probability, is 95%. So we can do 0.95, and we will get 1.96 as our z-stat. If we looked at the tail probabilities, we would type 0.1, we would get the same, and 0.25, and we would get the same answer, because 95% central probability is same as 5% of the area being in the tail. So we can either use this option or we can use this option. And this is a pretty flexible tool. No matter what our probability is, let's say we were to find out a 92% confidence interval, then our central probability could be 92% or 0.92. If it was 98%, then 0.98. So we can vary our probability and then get the corresponding z-stat. So applying this in our problem, we get 0.8 plus or minus 1.96 times 0.0447. And this will give us a value of 0.7217 at the lower end and 0.87829 in the upper end. So this provides us a confidence interval for the proportion of girls in the beginning skating class in the age groups of 8 to 12 at Ice Chalet. And again, with a 95% level of confidence, or our significance level being 5%. Now let's consider the problem of determining the sample size that will give us a desired margin of error. So let's say we want to conduct a survey, and the desired margin of error is 0.03 of the population proportion, and the survey has to be at a 98% confidence level. So how large should the sample be if it is anticipated that roughly 70% of the firm's cardholders carry a non-zero balance at the end of the month? So are interested in figuring out what percentage of people carry a non-zero balance, and suppose our proportion we've estimated is 0.7. So our P star is 0.7. In this case, I'll use P star. So our 1 minus P star is 0.3. And to get the sample size with the desired margin of error interval, our formula was alpha by 2 squared P star times 1 minus P star divided by E squared. And we can apply these numbers into our formula. We get our alpha by 2. Now this is a non-standard one, 98%, but we can use jump to calculate this area again. So we want 98% central probability. So here we get 2.2363. So we apply this in our calculation, 2.2363 squared. Our P is 0.7, 1 minus P is 0.3, and we divide this by a margin of error, which is 0.03 then squared. And when we calculate this, we obtain the value of 1,266.74, or our sample size should at least be as much as 1267. If we want to have 98% confidence that our proportion is plus and minus 0.03 of the actual proportion. So again, another practical application of this idea of confidence intervals, we can use N and P to calculate confidence interval, but given the margin of error and the confidence interval or level of confidence, we can also determine the minimum sample size required to obtain that margin of error.